a lot of good features. Okay. Now, electrical machine, we have generators. This is defined as the conversion of mechanical to electrical. Okay, we have motors. The opposite, electrical to mechanical. Okay, so this is the basic conversion between two types of energy, mechanical and electrical. Okay, and finally we have a third one, transformer, which we'll talk about on its own chapter. This is basically the conversion of electrical energy, electrical to electrical, different voltage levels. Okay, so it's AC. Okay, they don't relate to the conversion between electromechanical, but we put it here. So all these three are what we call electrical machines. Okay. Now the reason we put transformer in these, two groups is that because they work on the principles of the magnetic field. Okay, so that's what we're going to talk about today. Okay, I guess everyone knows what is a magnet is. Okay, has two pole, always two pole in real life. Okay, in theory there's a monopole magnet. Okay, it's got a north and a south. Okay, and between them it produces a magnetic flux going from north to south. Okay, so if I have two pieces of magnet, permanent magnet, facing each, well, you got to know the basic, right? I don't have to explain, if it's opposite pole, it attracts. If it's the same pole, it repulses, that stuff. Okay, but now if I have two pieces of magnet stationary fixed on two sides like this with opposite poles, what you are going to get is that there is going to be a flux line between these two. In real life, it's going to like bulge off, sort of like that. But when we draw this, we're just going to get rid of the fringing effects. These red lines is what we call the magnetic field. Okay. And the symbol of magnetic field, this is like a kind of like unofficial name. Okay. The official term for the magnetic field is what we call, written here note, magnetic. So from now on, I'm going to write MAG for magnetic, flux density. Okay, this is the official term. And most of the time, in most textbooks, the symbols that we use is capitalized B. It is a vector quantity. It needs, magnitude and direction. So this is the magnetic field. Okay, magnetic flux density. So it means that when you have two poles of magnet facing each other, it will produce a flux line. This red lines is called magnetic flux. Think, if you want to compare it, it's kind of like a current, sort of. You can think of it like that, between positive and negative polarity, sort of like that. The symbol that we use is phi. Okay, the unit of magnetic flux is in Weber. Sorry. Acronym is capitalized WB, which is Weber. Okay. So magnetic flux density, the unit is in Tesla. There's lowercase in honor for Nikola Tesla, or capitalized T. Sometimes it can be in Weber per meter square. Same meaning. Okay, because this is flux density, so it is actually phi divided by the unit area. We will come back to this later. So I'm just introducing you what is a magnetic field first, okay? Now, before we go into details about magnetic field, you need to know 4 basic principles relating to this magnetic field, okay? Principle number 1, current carrying conductor or wire produce a magnetic field in the area around it. So if I have a wire or a conductor showing you in black cylinder shape here, this wire has a current I inside it. This wire will have a magnetic field around it shown in the blue ink, okay? And which way is the flux flowing? In this case, it's clockwise direction. How do you do that? You use your, I think in English, it's called the gripping right hand rule, okay? So here my thumb points to the directions of the current. In this case, kind of like outward. All your fingers are the magnetic flux. So in this case, this is the cross section of the wire. So your current would go into the page. So it goes into the page. So your magnetic flux would flow counterclockwise, shown here. And if the flux would produce the magnetic field around the wire. Okay, so the wire is that black. I'm not sure you can see between blue and black. So this is rule number 1. Principle number 1. It means that if you have a, special eyes that you can see a magnetic field, you see it around you, okay, in our modern world, because, your phone has a current, has a conductor, the lighting in your room would have a conductor, all those stuff. You see a lot of magnetic field all around us, okay? Even your Earth has a magnetic field. We'll talk about that a little bit later. I think, do we have that lecture now? Okay, it's part of the first lecture you can look at, okay? So this is principle number 1. Number 2, this deals with us more directly. So this is a general term. So now we kind of like know, hey, if I have a conductor, I put a current inside that conductor, I get B, which is what I want. Remember, this thing is very important to us. Without this B, you will have no electrical machines. Actually, without this magnetic field, our comfort life would stop to exist. Okay, all the things that you know around you are mainly related to the magnetic field. Okay, your phone, your tablets, electrical power, most of the modern comforts that we know today relies almost entirely on the magnetic field. Okay, there's several movies in the past coming out. What happens if you have this no magnetic field world? Kind of like that. They have a term like electromagnetic pulse bond that doesn't kill people, but it destroys the magnetic field. So all the things that we know would stop working, no electrical power, no computer, all that stuff. So this is like very important. But we see we can generate current. We put the current into the wire, which is usually the case. You get a magnetic field. See, even the magnetic field even happens in nature. Okay. Since the Greek time, I think, coming from, people just found out that it's from asteroid of the Earth, falling, and it has a special property that attracts certain metals. So they know that's a magnet. And again, one of the, what do you call it, in China, one of Chinese discovery or invented, I guess, I don't know what is the term. One of them is the compass. So the Chinese people in ancient time using, natural occurring magnets to make a compass to navigate, the sea, the land navigations, okay? So we've been using magnets ever since, okay? Second principle, okay? This is related to our machines now. If you have a moving wire, okay, in the presence of a magnetic field, now you need a magnetic field. What's going to happen is that you're going to get a voltage induced in it. Okay, know the underlying letters, words, moving, mechanical. So you're moving some conductor inside a magnetic field, you get a voltage, electrical. So this principle is the basis of generator's action. Okay, so showing you here in the bottom picture, I have two magnets. Opposite pole generates the blue magnetic field B. I have a conductor or wire in red here. I move it into the page, kind of like three-dimensional with certain velocity. If I have a voltmeter that can measure both ends of these conductor or wire, I get a reading of that voltage. See, I get a voltage induced. Now, I was explaining a little bit later, because some move in some direction, it's not going to do that. Okay, you have to move into certain directions. Okay, in this picture, that would work. Okay, so this is the basis of generator's action. So this is our number one machine now, type 1 generators. The opposite of that, instead of moving the conductor or the wire, instead you have a current carrying wire or conductor. See, underlying current. If you have a current carrying wire in the presence of a magnetic field, you see the word magnetic fields again, would have a force induced on it. Okay, you see what you get here? Input is the current. What you got is a force, electrical, mechanical. You convert from electrical to mechanical. This is the basis of motor action. See, so this is our second type of electrical machines now. Now, I didn't say if it's whether DC or AC. We'll deal with that later when we deal with, what kind of current do we put in or what kind of voltage do we generate. Okay, so it can both be AC or DC. So again, same setup, same conductor, but this time I don't move it. Remember, in the second principles, I move it into the page. Now I don't do anything. Not really. What I do is that I don't move it, but I put a current into that conductor. I will get a force on this. It will move. Didn't show you the directions here yet. Again, we deal with that details later. Okay. So this is the motor action relating to the second type of our electrical machine. The fourth principle, as you can guess, we deal with the transformer action. Okay. Now, what I want to point out is that the second and the fourth is kind of like a similar. We don't really look in details. Okay. The fourth one, it says a time-changing, varying magnetic field. See. Now, emphasize on the term time-changing. What happens if you have a time-changing magnetic field? It's going to induce a voltage in a coil of wire. The coil of wire determined for us is what we call a winding. If it passes through that coil, okay? Now, this is the basis of transformer action. Now, important thing here is that it has to be time-changing. In order to get a time-changing magnetic field, the only way that you're going to get that is AC magnetic field. So I'm showing you here, the blue is the magnetic field pulsing. I can't do that on a stationary drawing. Okay, so it's go up, down, up, down, up, down. So what I show you here is the vector B, the magnetic field, as a function of time. It varies as a function of time. Okay. If that happens, if I can generate that, I put the red coil in there, windings in there, showing you in the red curly thing here. If I do that, I don't do anything. I just put it's stationary, not moving. The magnetic field is stationary in a physical world, but it moves according to time, right? Okay, a function of time, pulsing. Okay. If I measure both ends of these windings, I get non-zero reading. I get a voltage induced in the coil. Okay. Now don't get confused with principle number 2. Number 2, I get a voltage. If I move the wire or the conductor, here I do not move anything. Okay, I just put it there, but without moving, my magnetic field has to be a function of time. So this does not happen in a DC world. Okay, So that's why this is the basis of transformer action. So when we talk about transformer, these are AC electrical device or electrical equipment only. There's no such thing as DC transformer. Okay, so don't get confused. When we say transformer, that's in an AC voltage system only. Okay, step up the voltage, step down the voltage. Okay, no moving part. Nothing's moving. Sometimes called static equipment. Okay, so these are the four main principles. Okay, focus on 2, 3, and 4 are our basis of the basic principles of our machine that we will study. Okay, now back to the first one. Remember all these 1, 2, and 3. We have the word magnetic field, magnetic field, magnetic field, and magnetic field. You need magnetic field no matter what. And we know from number 1 principle, you do that pretty simple. A current in the conductor, you got that. Now, problem with this is that it's not really strong. Okay, right now maybe on your desk, next to you, you have a phone. That phone will generate a magnetic field, but it's very, very weak. Okay, and if it's very weak, that's not usable. Too weak. Okay, so we can make it stronger in order to utilize it to to make the electrical machines that we want. Okay, so we go to the next topic. It's the production of a magnetic field. Okay, now magnetic field can be formed two ways. I can use a permanent magnet, man-made or natural magnets. Okay, and you get a magnetic field. The problem with this is that you can't really change its strength. It's fixed. Okay, and we don't like that. Or you can come up with two pieces of electromagnets. Okay, give me a second. Okay, so we need electromagnets to do that. So now let's look at the production of a magnetic field first. Okay, the law governing the production of magnetic field is what we call Ampere's law. Remember Ampere, unit of the current? Okay, it's somebody's last name, a Frenchman's last name. I just Google that, Andre Marie Ampere. He's like a pretty smart guy. He had this law that says, okay, very scary law. Okay. Integration sign with some circle on it. This is what we call closed surface integration of vector H dot dl equals to I net. Okay, don't get scared by this. I'm just showing you, it looks scary. That means you can have a magnetic field for any given shape or form using calculated using this law. But ours are more, simple constructions. Okay, so what we need is this thing. Okay, I call this a square donut. Okay, these are made with ferromagnetic material. Okay, ferromagnetic. So it's a material in the ferrite family. Ferrite is Latin, okay, meaning iron. So any material that has in the iron family, like steel, cast iron, would be a good material to make electric machines. Okay, we'll talk about that a little bit later. Why it has to be this family? Why not copper? Why not silver? Why not something why not something else? Well, lucky for us though, iron is probably one of the most abundant materials on Earth. So that's fine. Okay, it is also a good material for making all these electrical machines that we know today. Okay, so this ferromagnetic material forms a shape. Okay, square donut shape, rectangular donut, whatever it is. Okay, then we're going to make, well, we're going to make this into a magnet. But how do we do that? If it's a pure iron or pure steel, What do? You wrap a winding around, okay, one side or many sides if you want. Okay, I'm just doing simple one here, one side. So this wire, okay, has n turns. Now, in practice, each loop, each turn is not electrically connected. That means the wire has to be coated, okay, insulated. They usually have enamel coating on the wire. So that means if you want to do this at home, you cannot just get, you know, a regular cable, electrical cable that you have at home and strip off the insulations and do this. That won't work. The copper has to be coated with enamel, some thin film to prevent, you know, to have electrical isolation. Has to be specially made, okay? And you loop this in terms of, you know, winding for n turns, okay? So that's what we can do with, okay? You do this in n turns, and then you inject a current into that windings. What's going to happen if you do that? Notice that principle number one goes here, because each turn here, I can kind of like zoom in on my turn. So this is my iron. Then I have one loop here. Okay, the current goes like that. Then goes back like that. Okay, I'm gonna do like let's do 3 or let's do 4. Okay, so each would have a current. Now using your right hand rule, the current goes that way. You're gonna have a magnetic field around this. Okay, each windings. Okay, but each one would help one another. Okay, forming a bigger loop. Okay, and that's going to generate the total magnetic flux going that way. Okay, how do I know which way it's going? Use your right hand rule again, but this time these are the fingers. The direction of the flux is your thumb, so this is the fingers, goes up. Okay, so it shows you here my feed, this blue path would flow in a closed loop in the core, in the ferromagnetic core. So if I have a flux, I can have a magnetic field, okay? And as it turns out, when I perform this structure setup, I can determine the relationship based on Ampere's law, okay? Meaning what? If you look at this, re-express this, what I would get is that this equation, H times LC equals to N number of turns times the current in each turn. Okay, that's the meaning of I net, net total current. In this case, why does it have to be N times I? Because each turn is individual, but the total forms the net turn. Okay, so this is what I have. Now, what about H and LC? H, it's a vector. I'm expressing in scalar or the magnitude here, but it's a vector of the magnetic field intensity. Now, don't get confused now. Now, we have 3 terms now. Earlier, we have, where's my note? Earlier, we have the term only magnetic field, a true word, which is B. So the same thing as magnetic flux density, so this is the same. Now we have magnetic field intensity, okay, intensity, okay. Now this is like a very abstract term, okay. So your textbook gives you a very good, you know, a very good explanation, description of this. You can think of this H as a measure of the effort to produce phi by the current I net. Okay, the effort, sort of like that. Think of it that way. I'll come back to that later. Okay, okay, and then vector L, which in scalar form translates to L sub c, is the vector of the magnetic path length. Okay, how long does the magnetic flows? In this case, you can measure in our structure LC right away, right? You know the dimensions of the core, you know, all four sides can measure. And Inet is the total current in the windings. I talk about that, which is number of turns times each individual current. The unit of Inet is A dot T, amperes turn. Okay, this is amperes turn. Okay, T is turn. Okay. Now, if you look at this equation carefully, okay, the H, the effort, can be expressed like this. N times I divided by L sub C. And the units of H is amperes turn per meter. Okay. Now notice that this equation, or this original one, doesn't have to do anything with the materials that made up of the core. See what I'm doing here? Meaning if I have this structure, I have two structures, A versus B. A, my structure is made with ferromagnetic, let's say iron. My structure B, same dimension, everything is the same current, same wire, everything, but the core, one is made of steel or iron, the other one is made of plastic. Okay, notice that it's just, if they are both the same dimensions, aside from the core, if I calculate H for each one of them, it will be the same. Notice that? See? Because in this equation, there's nothing telling me about the core material. So it means it will produce the same effort. Okay? It's like assuming we can measure the effort of the student. Okay? If everybody students put the same effort in this class, not all the students going to get the same grade, right? You say, you can say, hey, I study for your exam 2 weeks. The other guy says 2 weeks, and the girl says 2 weeks. All three are not going to get the same grade. Why? Because individuals have different IQ, right? See, you see. So this is where it plays. So this only is the measure the effort. Okay. The one that's more important is the core material. Okay. That's why we don't use H. We don't use effort. We use magnetic field or flux density. So the strength of your magnetic field flux, which is equivalent to flux density, which is your magnetic field B, produced in the core, also depends on the materials of the core. Okay. And how does that relate it to H? Your B is equal to mu H. Okay. Now this is where mu, or the core material, matters, because mu, this is something new, is what we call magnetic permeability of the material. Okay, the unit is Henry per meter. Okay, mu is something occur in all materials in this universe. Okay, but its value is very, very low. Many zero after the decimal points. Okay, so let's say 70. You're tired of writing it. Okay, so instead of expressing it, actually there's a way. Scientists found a way to find out the permeability, kind of like the minimum permeability. We call that mu naught. Okay, this is like absolute zero in thermodynamic or in temperature measurement. Okay, 0 Kelvin. Okay, same thing here. We have the term what we call mu naught, is the permeability of free space. Turns out that it has a nice and compact form in terms of 4 pi times 10 to the minus 7 Henry per meter. Okay, so if you look at this, permeability of free space is very, very small. You can, punch a calculator and get these values. It's going to be like 70 after decimal point. Okay, now, because we know each material has a very small permeability, so we compare with this reference, is minimum, and we call that relative permeability. Okay, because this is a more convenient way. Divide the value of your actual value divided by mu naught. We give you a larger number, easy number to write or express. This is used as a convenient way to compare magnetizability of materials. Okay, now let's see, what are these numbers? For example, steel using electrical machine has a mu r in the range of 2,000 to 6,000 times. So you see how small they are? 6,000 times. Let's say I use, let's exaggerate. Okay, if my mu r of my iron is 10,000 times. Notice that mu r has no unit. It's about how many times, because h over m cancel. Okay, the actual mu iron is equal to mu r of iron multiplied by mu naught. So it is equal to 10 to the 4th times 4 pi times 10 to the negative 7th Henry per meter. Rewrite this is going to be 4 pi times 10 to the negative 3rd. So you see it is still very small. See? So it is easier to express as, 10,000 times, 2,000 times, 7,000 times, whatever, how many times. A lot easier, a lot more common tricks to do. Henry per meter, don't forget. So this is, remember, these are good material. Ferrite family, ferromagnetic. Mu r for other non-ferromagnetic materials are 1. See, this include air. 1 meaning what? Almost the lowest value. It's the same as free space. So meaning I have 2 core material. Example we just talked about. One is made of iron. 2-dimensional drawing here. So this is iron. Another one, same dimension, same windings, same current. This is made of plastic. Okay, same H. H here. Let's make this A. This is B. This is A. HA equals to HB. You get the same effort. But BA would be equals to mu iron times HA, while BB is equal to mu plastic times HB. Okay, and this is, compare these two, assume like on average, so let's say 5,000 times. This would be mu iron is larger than mu plastic 5,000 times. So I get 5,000 times stronger magnetic field. You see how that works. So that's why you never seen any electrical machine made of other materials than the ferrite family. You cannot make motors of plastic, of copper, of wood, paper, anything doesn't work because their mu is very small. See, so magnetic permeability plays an important role in generating the magnetic field that we want. Okay, that's why you never see magnets, magnets, man-made magnets made of other materials. There are other, they call the high mu material made of ceramics, a compound, but those are, let's forget about it. Those are more high end, but they are related to ferrite in the composition. Okay, but all non-ferrite family cannot make magnet. Doesn't generate strong magnetic field. See? So once we understand that, back to our core, for the core shown, then you can determine B, which is what we want. We don't want H. We don't care H as much, but we're going to use H. We can calculate the magnetic field from our structures using this equation. We found H earlier. Substitute H in there. It becomes mu Ni divided by LC, showing you in the box here. Mu Ni divided by LC, where mu is the core materials. Okay. So now we can generate our magnetic field now for a given structure. Okay. Now, we can also apply this to determine the flux, okay? And the total flux in a given area is given by this equation. Again, don't get scared by this, area integration of phi, but this is a, a flux equation in any, form or shape. Closed surface integration of magnetic flux, magnetic field dot dA. We're not gonna use this because in our class, in our course, we assume perpendicular flux to the plane of the area. Okay, so meaning if I have a, let me get a scrap paper. If I have a piece of core, ferromagnetic core, like that, I would assume that my flux is going to be going perpendicular to the plane, 90 degrees to that plane. Okay, that's our assumption in this class. If we do that, we get a nice and simple expression of phi. Phi is actually equals to B times A. Simple as that. Okay, and if we do that, because we know B earlier, substitute B back in the form of mu Ni over L, you get the magnetic flux is equal to mu N times I over L times A. See? So notice that if we have a core right here, our square donut core, if I know its dimensions, like length, width, and height, I know how many turns I have, I know how much current I got. I can calculate number 1, B. Number 2, flux inside that core. See, notice that from that equation, this is B. I know mu because I know my material type. I know how many turns, I know how much current, I know the length. See, if I know the dimensions, I would know the area. I can also determine phi. See, but again, most of the time your machine is not like nice looking shape, simple as this. Okay, so we need a better way of calculations. So we came up with a better model. Okay, what we call is a magnetic circuit. So remember, your machine doesn't look a square donut shape. It's going to look something stranger, like a cylindrical shape. Okay, that you see in a motor generator. So the ways to calculate your magnetic flux and magnetic field is going to be more complicated, and this will take a longer time. So we have this magnetic circuit model instead. Okay, now the term magnetic circuit is using the same concept as Ohm's law in electric circuit. Okay, now what I wrote here, I shorthand lots of my writing. Circuit, I use CKT. Okay, electrical or electric is ELEC dot. Okay, in Ohm's law, what do you have? You have 3 parameters, right? A voltage source, a current, a resistor. And Ohm's law gives you V equals to IR. Everyone knows that. Okay. Now, here, your voltage source, the official name in electromagnetic field engineering, this is called electromotive force. I think you've seen this in physics, maybe EMF. Okay, that force gonna pass through a resistance of a circuit. In this case, it's a resistor R, and it passing through in the forms of the current. Okay, so the current in the circuit, R is the resistance of the circuit. Okay, so we do that, express this in a table manner. This is electric circuit. We have what we call a driving force. It's like the source of your circuit. EMF, this is a voltage. The impedance of that circuit, what impedes that force, is a resistor, a resistant, R. The response from that impede or that resistance is the current, I. So you know this. You know this already. Okay, this is what we got Ohm's law. Okay, we adapt the whole logic here, the whole concept here to what we call a magnetic circuit, the one on your right. Okay, now in your magnetic circuit, remember our focus is magnetic field and magnetic flux. If you have magnetic flux phi, you get a magnetic field B. Okay, again, don't forget that. We want that. We got that. We got that. Okay, so in a magnetic circuit, you have three elements also. You have the source. In this case, what we call is electromotive force. The symbols that we use, a curly F, I think. Okay. It is equal to what is generating in your structure. What generates that? Go back to our structure. What generates flux is this current and this N turns, right? Your I net, this thing here. So we call that the magnetomotive force. N times I. See, that's the source. Okay, so your driving force is MMF, magnetomotive force, which is N times I. The symbol that we use is this thing, the curly F. Okay. What's the impedance of your circuit? We give it a new name instead of resistance, just to make a distinction. We call that a reluctance. We'll talk about that in a moment. A curly R. Okay. The response from that impedance is flux, your magnetic flux phi. And we use the same concept from Ohm's law. So we get N times I, which is your force, equals to the response time the impedance, which is phi times the curly R. And if you re-express this in a curly F, you get this magnetic circuit relationship. Magnetomotive force is phi times reluctance. Okay, so this is what we got from the magnetic circuit, using a simple concept from Ohm's law in electric circuit. Okay, but don't get confused. This is the magnetomotive force. It deals with the current, but we're not going to use that. We use magnetic flux. Okay, now, so our important part is what is the reluctance, what impedes in our magnetic circuit. So if you look at this, compare this carefully, you have potential or voltage, you have a resistance. This resistor resists the flow of the current in electric circuit. See, you see how that works? Okay. Again, in analogy, you have magnetomotive force, you have impedance, what we call reluctance here. This reluctance relax the magnetic flux, kind of like impedes. Okay, if you think a magnetic flux is like a water, this is like the size of your pipe. Okay, high reluctance, small pipe, so the water flows slower, well, not slower, harder. Okay, larger pipe, easier. So that's form of reluctance. Think of it like a resistant, but that it doesn't resist the current here, it resists the magnetic flux. Okay. Okay, now what is a reluctance? Turns out that from your derive of your magnetic field and using the magnetic circuit. Let me grab a scrap paper. Okay. So earlier we say, hey, N times I, E goes to phi times the curly R, which equals to that curly F, right? So reluctance here is equal to N times I divided by phi. Nothing complicated here. See? So the units of your reluctance is going to be amperes turn divided by Weber. Important here, don't forget. Okay. And it says here that reluctance of the core material resists the flow of the magnetic flux. I just explained that previously in a magnetic circuit. Similar idea to that of resistant electric circuit. Now, what happened is that we are using this similar analogy to electric circuit. So all the features, all the law applies in this magnetic circuit, meaning what? Reluctances obeys the same rule as the resistances in electric circuit, meaning for series reluctances, its equivalent value is the sum of all the series components. So Req is R1 plus R2 plus RT, just like a resistance added together. See, you have R1, reluctance 1, reluctance 2, reluctance 3. It forms this Req, which equals to the sum of the 3, right? R2 plus R3, series. Similarly, you have parallel. You do the same calculations. See? So you have parallel reluctances like that. R1, R2, R3. And again, this turns into R equivalent. 1 over Req is going to be 1 over R1 plus 1 over R2 plus 1 over R3. See? Same rules, like a resistant. Okay. To give you an example here, you can study that on your own. Nothing complicated there. Okay. Now, how do we find out the values of our reluctance? Okay. Before we do that, let's look at this model we have. So if you look at this model, the magnetic circuit is very simple. If we somehow can determine the reluctance's value, okay, but there's a limit to this kind of model, okay. So calculations of magnetic flux that we just talked about using the magnetic circuit are always approximation. You never get exact answer. There are other ways to do that. A more advanced math like finite elements, you know, all those stuff. Okay, you can get a better calculations. But you know, for our introductory class, this is okay. And sometimes that's good enough approximation. The reason being is number one, we assume magnetic flux is confined within the core. Okay. In real life, it's not true. In reality, there's always a leakage flux leaving the core into surrounding area. Okay. So for us, we assume it's here inside. Actually, they are bulging out. See, these are what we call leakage flux. Okay. For us, we assume, hey, if this is the core, your magnetic flux goes there. Nothing coming out. In real life, there are other parts going out. We don't take that into account. So that's our assumption. Okay. Number two, we call these leakage flux, by the way. Number two, calculations of core reluctance, which we do that later. Okay. assume a certain mean path length. Okay, let's say I want to calculate the length of the core like this. A corner of a structure. I would assume that the flux flows like this. 90 degrees angle. So it's easier to calculate the length, right? In a real world, the flux doesn't really, hey, turn 90 degrees. Usually it's going to have a curvature, you know, like you're riding a bike. Can you turn 90 degrees on a bicycle? Even a car, you can't do that. You need a radius to do that, right? So in a real world, it doesn't happen that way. So, but we assume it's, you know, right 90 degrees. So the mean path is only approximation. Okay. Number 3, permeability of the core is assumed constant. We talk about that mu, right? And if we mention hey, if it's constant or not, actually in the real world, it's not really constant all the time. It depends on in the environment, in where you use it, stuff like that. But our assumption assumes it's constant. Okay. And number 4, which is our main concern in all these assumptions, is that if there are air gaps in the flux path, okay, what is air gap? Your core that we draw earlier. Okay, if this is my core, give me a second. The battery is low. I'm gonna lower the brightness of my screen. Okay. So if you can't really, hang on a second. If I'm off screen or something like that, just let me know, because I'm lowering the brightness of my screen. I'm not gonna look at my screen now. Okay. So if you have a core like this, okay, and then you have the windings over there, you generate a magnetic field that you want, but it's not useful. It's just a magnet. There's no spinning part, okay? So we need to somehow separate this, okay? Turns out that the earlier model, the design machines actually, motor that Edison built, similar like that. You can Google search the earlier version of the Edison's motor. One of them is going to look, I'm trying to sketch, not as good. It's going to be something like this. You're going to have he's going to have a core similar to what we have, but one side of the core is going to be cut open. Okay, and then you can have the rotor in here. So there's an air separating between the two pieces. So when it's stationary, during the magnetic field, this one is going to spin. Maybe you hold it with a shaft, kind of like, so it's going to spin. See? So you need air gap to separate between the stationary and the moving parts. So that means in the 2 electrical machine, motors and generator, you need air gaps to do that. That means air gap is inevitable for us. So if there are air gaps, when there's air gap, your flux path is going to change. The effective area of the air gap will be larger due to what we call fringing effect. Drawn here. If this is the air gap, our assumption, assume that, I'm zooming in. If this is my air gap, okay, I assume the flux flow like this in the core. Okay. In real world, it's going to go out just like that, leakage flux. Okay. We neglect this part. This part is what we call fringing effects. See the bulging part. We neglect that. Okay. Because if we include that in there, the flux, the area of the path is going to get larger. See? So that's why magnetic circuit calculations are always approximated, all these 4 reasons. Okay. Now, reluctance, how do we find them? Okay. So using the magnetic circuit equation, we express here magnetic force, which is N times I divided by phi, and we know phi already earlier from your magnetic field, which is H LCI net, right? So put it there, mu C of the core times Ni divided by LC times A. Put that back in the R. What you get is going to be a nice simple form. Reluctance is length divided by mu A. In this case, length in the core, mu, which is permeability of the core. Symbols that. Okay. So let's do a basic example here. Okay. I have a structure, square donut, two-dimensional drawing here. Okay. But this time my donut has an air gap. I know the dimension of the air gap, G here, 0.05 centimeter, pretty small, right? Have a millimeter. Okay. Now, I know the dimensions. I get LC is 40 centimeter. Okay, I know number of turns is N, the current I. Okay, and I know the cross-sectional area of the core, which is giving us 12 centimeters square, and it's 400 turns. Assume the core permeability is about 4,000 times. Okay, now, in this case, we talked about that the moments ago, that fringing effect is neglected. In this example, not neglected. The problem states that fringing effect increases the effective cross-sectional area of the air gap 5%. So you have to take that into account. This problem is asking for two parts. A, total reluctance of the flux path. B, the current required to produce flux density of 0.5 Tesla in the air gap. Okay, so we will change this into a magnetic circuit. The ways to do that, number one, look at the path of the flux. How many paths does it have? Okay, in this case, one path only. Number two, look at how each path, in this case one, how many material does that flux is passing through? So in this picture, it's passing in the core, that's one, in the air gap, which is air, that's two, you see? So that means to sketch this magnetic circuit, you have magnetomotive force, which is N times I. You have your flux, okay, passing through one material, which is the core itself, R sub C, and then the air gap, R sub G, because the same path, so both are in series. So you can sum these two to get the equivalent resistance. Okay, so far so good. So first you look at the path of the flux. How many paths? One. Each path, in this case only one. How many material does it pass through? In this case, it's flowing into the iron, or we don't know what it is. Okay, the core, and then the second, the same path in the air, and they are in the same path in series. Hence the circuit here. Okay, we draw this magnetic circuit. I didn't do that there, but you can do that in an easy manner, right? Simplify this, you get something that looks like this. Simple circuit, REQ, where REQ is RC plus RG, and this is your magnetic flux. This is N times I. You know N, you know I, okay? You want to find REQ, you start with RC, okay? So RC, using this rule, length divided by mu A. So you need length of the core, LC. Now, notice that this is 40 centimeters or 0.4 meter is a whole loop. you want to make it precise, you can minus 0.05, but that's not going to give you a difference of the answer as much. So we can neglect G. If we know that LC is a lot larger than G, you can neglect G. You don't have to subtract. So this is kind of like approximation also. You want to make it right, you can minus 0.05. No, not 0.5 times 10 to the negative 2. But your answer won't change as much, right? Okay, so I can use that. Mu C, which is mu RC times mu naught, and then AC, the cross-sectional of the core. You know all these numbers, right? You know mu RC is 4,000 given by the problem. You know mu naught value for pi negative 10 to the negative 7. You know AC given to you as the 12 centimeters square. Don't forget to convert into meters square. This is centimeters square. So to do the conversion, again, I emphasize these points a lot because a lot of the time in the past, students make these simple mistakes, which is not a good, in my opinion, that's not a forgivable ways to do, okay? So you gotta make sure that you know how to do the basic conversion, you know, like high school students can do that, even elementary school. So your engineering students, you shouldn't do that kind of mistakes, okay? So you have to know how to convert from square centimeter, centimeter squares to meter square, all that basic stuff, or centimeter to meter. Don't forget, okay, important point here, okay? Because you're gonna change all the numbers, and that happens every semester in the past. You don't want to be that students, please, okay? So be more thorough in your, you know, in your work. So here, I was given 0.4 meter, mu R 4,000, mu naught, AC in centimeter square, convert to meter square. Calculate that, you get this number, okay? Do the same thing for the gap. See, the flux pass through the gap, only this black ink, very short length. So the flux length in the air gap is going to be this gap. See, 0.05 times 10 to the negative second meter, convert from centimeter to meter. And because it's air, so relative permeability is 1, not in here. So just mu naught, Ag, the area, the effective area of the air gap. Now, because we do not omit fringing effect, the problem states that fringing effect increases the effective cross-sectional area of the air gap by 5%. So you have to take this into account. So it is equal to 1.05 times AC, the 5% into account. You know AC already, so just multiply it by 1.05. Calculate that, you get that number. Now, before we move on, you compare between these two. These are reluctance, like a resistance that impedes the path of the current. This impedes the path of the magnetic flux. That's very big compared to that of the core, you see? Even though the gap is very small. See? It's like 300,000 amperes turn per Weber. This is like 66,000. Almost 5 times as large with a small air gap. You see, if the gap is the same size, it'll be like very, very big. See, that's why if you have a, where's my picture? For a second. See, that's why if I have magnets, if this is like further away, this is air, let's say 10 centimeter, you barely have a magnetic field. It's going to be very weak. See, if it's passing through air, your magnetic flux will be very, very small. I'm sorry, magnetic field, flux density will be very small because your impedance, your reluctance is going to be very big. But if you get that inside the core, comparing, it still looks very big, right? But that's a lot smaller compared to air. See? And again, instead, if I don't do this with iron, I do this with, maybe wood, plastic, I get rid of that 4,000, it's going to be even larger. You see what I'm saying here? That's why the core of electrical machine, all electrical machine has to be ferromagnetic materials. Without ferromagnetic, you don't get that high relative permeability value. Once you get these two, you can determine REQ, add them together, you get that number. And I put here, notice that RC is a lot smaller than RG. Okay, so what is the problem again? Total reluctance of the flux path, we got that. This is REQ, so that's part of the answer. Now part B, current I required to produce the flux density of 0.5 in the air gap. Okay, so once we got the reluctances, we utilize the magnetic circuit again. Flux density in the air gap is Bg phi divided by Ag. Don't forget. And the problem states that Bg has to be 0.5 Tesla. You can use the equation to calculate what phi is required. So phi is 0.5 times Ag. And we know Ag earlier in part A, so you can determine phi. Okay. Once you got phi, you can determine the current. See, using the magnetic circuit equation from this, magnetomotive force equals to phi times REQ. Okay, and this is equals to N times I equals to phi times REQ, shown there. So therefore, your current has to be phi divided by REQ over N. Okay, and we want phi. Phi has to be in terms of Bg times Ag, the requirement for the problem. And we found that out. So substitute all the numbers in. 0.5 times Ag, which is phi times REQ divided by the number of turns, you get 0.602 amps. Okay.
อาจารย์ครับ
Yeah.
The slide มันหายไปอะครับ
Oh, hang on. My battery is really low. They just asking me. Okay, is that good?
ครับผม
Hang on. How many percent do I have? 5. Okay, should be. Yeah, I'll try to finish it within time. Okay, so now go back to the notice that I say about. So this is the exact answer, taking into account all reluctances. Okay, now because we know RC is a lot smaller than RG. Okay, we can, let's say if it's a lot smaller, we can neglect RC. Okay, because of this reason, about 5 times. Let's say we do that, then your REQ. I kind of skip this part. If we assume this, that, then your REQ is approximately equals to RG only. Actually, it's RG plus RC, right? But if we omit that, we assume it's 0, it's equal to RG. So if you do that, you can substitute REQ equals to RC. REQ equals to RG in there, which is shown here. Instead of 382,000 is 315,000, using only RG value here. Recalculate the current again. Turns out that you get about 0.498. And if you compare with 0.6, this may not be a good approximation because this is not really true yet. Okay, there are some problems that this is true, so you have to look. Okay, so we look at that, but the key point here is that most of the time this is true. RC is always going to be a lot smaller than RG, where you can neglect RC in the calculations. Okay, not this problem though. Okay. There are second example that you can study. Okay. Now that's a simple one. Hang on a second. Let me grab a charging cable. I'm not going to be able to finish everything in time. My iPad's really old, so hang on a second. Move this a little bit. Okay, so that's better. Let me. Okay. Okay. Where am I? Second example. Okay. The first example, the structure is very simple. The most basic one. Let's look at second example. Okay, pretty messy here, but try to zoom in and look at it. We have this time we have a more complicated structure. Okay. This is what we call a three-legged magnetic core. Okay. So it's, if you look at the two-dimensional drawings, let me try that. It's going to be something like this. It's like a T in the center with two air gaps. Kind of like that. Okay, that's what's shown here. I'm showing three-dimensional drawings. Okay, two air gaps on each side of the leg. So this is called three-legged magnetic core. Left leg, center leg, right leg, with the windings in the center leg. Okay. Now, so you should study this, but here if you cannot read anything, just tell me. Okay. We'll go through this a little bit. We'll come back and revisit next time because I won't be able to finish everything within the time that we have. Okay. Now, what we have here is one coil in the center leg with 300 turns, and the current in that coil is 1 amp. Okay. The dimensions. Hang on. I'm sorry. I have a picture of this. Example 2. Give me 1 second. I should post that up. I keep forgetting. I'll do that later. Okay, but 1 second. Now, 1 second. One moment. Okay, I'll post the whole problem, the whole wording problem for you. Okay, in a more readable manner. It's just a screenshot, but here I'm just gonna briefly explain what happens. Okay, so this three-legged leg, we know its dimension. You don't have to write this down, and I'm not gonna post it. I'm gonna post the whole problem for you. So we know all these distances. Okay, know all of them. It's like 730, 730, and 7 all centimeters. 730 and 7, and the depth into the board is 5 centimeters into the page. Okay, So that means you can find out the dimensions each. And then a coil in the center. Okay, we know the gap. The left one is 0.7, 0.07 centimeter. G1, the right one is 0.05, G2. Okay, so we know its physical dimensions. Okay, now what we want to find is that we want to find the flux in each of the leg of the core. So we want to know how much flux is here, flux is here, and flux is there. Okay, again, the starting point is to sketch your magnetic circuit. Okay, and again, to start the sketching of your magnetic circuit, you start with the source and trace the flux path. Okay, so you start with the source, which is the windings in the center leg. So I'll do it here slowly. Okay. So my center leg, let's cover that. When I finish the sketching, we'll stop the class. So that way you can have a few minutes break. So here, so there's my curly F, N times I. Okay. It generates a flux going up because the curly fingers go like that. So it's going to go up. We call this phi C. I'm just labeling that center leg. Okay, so it's going to go up. Not upstream, right? Okay. Then you look at this. The flux split into two paths. One to the right, one to the left, blue and red. So you have to do that for the magnetic circuit. So one goes to the right, I'm calling this phi R. One's to the left, phi L. Okay, now each path, number one, phi C, your center, the flux is passing through one material, one, which is the core. So you have to put a reluctance in there, R sub C. See? So I take into account both the bottom into this one. On the right path is passing through the core, the gap G2, and then completes the path. So here, the core, R right, RG2, and then finish the path. See? Similarly on the left, same thing. R left, RG1, completes the path. You see how this works? You have to be able to do this. So this is what's shown here. Okay, so you must start right, but that's not enough. Okay, the next step is to find all the reluctances, which we cover next. Okay, but again, starting with your source, the magnetomotive force, N times I, and then look what's it's passing through. Don't forget the center leg. We're passing through this core. Okay, and on the right is going to be the core and the gap. On the left is going to be the core and the gap. Okay, we'll come back and finish this example next time. I'll send you the problem. It's at the end of chapter problems actually, but with the old numbers. Okay. All right. So don't forget to check your post, and then we'll see you again next week. Okay. Any questions before I log off?
No, sir. Thank you for today class.
Okay, I'll see you again next week. So stay healthy and stay safe, please. I'll see you next week. Bye.
See you, sir.
Thank you, sir.
For those of you who are just, show up today or log in today, don't forget to join the line group, okay? And next week, I'll come up with a list so I know who's who in my line group, okay? So if you know a friend who's taking this class, if they haven't joined, let them know, all right? Okay, bye.
Thank you, sir.
thank youครับ